So we're going to move on to our last type of integration. And before we look at that, again, I want to go back to the chain rule. Now, we've already looked at the chain rule at the start of this video, so I'm going to go through it quite quickly. So here are some examples of the chain rule, and I said to really think about them in terms of the composite function. So our f of x at g of x and how this was then f after g of x. Same here, f of x, g of x, and how this was f after g of x. F of x, g of x, and f after g of x. So we're going to use that idea and we're going to go a little bit deeper into it, and we're going to really focus on the formula of the chain rule and then how we can use that for integration. So not just basic examples like we had at the start of the video. So U-substitution for integration. So this is obviously often called just integration by substitution. You might find more resources on it if you use the idea of U-substitution. But basically, integration by substitution, which is also known as U-substitution, is a technique used to simplify integrals by substituting a variable within the integral. So we simplify it using substitution, hence the name. The technique is particularly useful when dealing with complex integrals, and it's particularly useful when dealing with composite functions or where the integrand contains a function and its derivative. So I suppose our focus is on composite functions, and I want to focus on the idea of that chain rule in a bit more depth, which will hopefully help you to understand this integration by substitution or U-substitution a little bit better. So let's explore using the chain rule formula from the log tables. So here's an example, y equals 2x squared plus 3x to the power of 5. So the formula in our log table is f of x is equal to u after v of x. So we're going to define two parts. We have a v and we have a u. So v is our inner function. So we can see we have v is our inner function, which is going to match here. So our v is going to be 2x squared plus 3x. Now, our u has to be defined in terms of v. So what that means is the whole function, so think of u as the full thing, is going to be v to the power of 5. So rather than writing 2x squared plus 3x all to the power of 5, we're defining u in terms of v. And the reason for that is if you look at the formula for the derivative, we have du dv, which asks us to differentiate u with respect to v. So we're going to have u is equal to v to the power of 5. So du dv is equal to 5v to the power of 4. Our v is 2x squared plus 3x. This formula tells us to find dv dx, so differentiate v with respect to x, and that gives me 4x plus 3. And then the final answer for the derivative is going to be du dv, which is 5v to the power of 4, times dv dx, which is 4x plus 3. And then we're subbing in for our v. So that is 2x squared plus 3x, and then 4x plus 3. So because we can do this a lot quicker, we tend to either not use the formula at all or move away from it as we become more familiar with it. However, the idea of using this formula is going to really help us as we try and move backwards because we use the same idea. Okay, so our steps for integration by substitution are choose your u, so select u as the part of the expression that will simplify the integral. Differentiate u, so find du in terms of dx. Substitute, so replace the original variable and expression in the integral with u and du. Integrate, so now that we have something that's much simpler, we're going to perform that integration, and then back substitute. So after integration, you go back and replace u with what you had originally. So one thing to note is you always want to sub back in before calculating your answer using the limits of integration. So when we have a definite integral, you always sub back in first. So let's use these steps and let's see if we can figure out how we integrate using U-substitution. So let's try some integration using U-substitution. Here we have the integral of 2x plus 3 to the power of 5 dx. This is a lovely straightforward little example, and we could probably do this using the skills we learned at the start of the video. just thinking about it logically. However, we're going to try and use this new technique, which is integration by substitution or U-substitution. So it's called U-substitution because we generally use the letter U to stand in to make the integral simpler. So we generally want to try and recognize that we have a composite function of some sort and that there is an inner function. So the inner function is going to be the one that we want to label as U. So in this example, it's going to be the 2x plus 3. So we're going to take that and define that as our u, which is 2x plus 3. So what we want to do with our integral is we want to then simplify it by replacing that inner function with just the letter u. However, because I've replaced the x with the u, I also want to replace the dx. So how I do that is I differentiate the u that I've chosen, so du dx, and that's going to give us 2. And then I separate out the u's on one side and the x's on the other. And specifically what I want to do is get dx on its own because I have a dx here that I want to replace in some way with a u. So I'm going to bring this 2 over the equals as well. So that gives me a half du equals dx. So instead of my dx, I'm going to plug in a half du. So what that ends up giving us is u to the power of 5 over 2 du. And now I'm going to integrate as normal. Add 1 to my power, divide by my power. So in this case, I'm dividing by 6. There's already a 2 here, so that's 12. And I'm also going to have a plus c because we have an indefinite integral. So now, before I finish, I have to go back and plug back in my u because we added in the u, so we need to make sure we take that out. So that means we're going to have 2x plus 3 to the power of 6 all over 12 plus c, my constant of integration. So example 10, integration by substitution. The first thing I want to do is, can we identify that it's substitution? Now, at first glance, you might say, is this not integration by parts because we have multiplication? That is absolutely true. However, what we want to identify first is, do we have a composite function? And we do. And we can see the composite function piece right here. So it should be e to the power of x, but we've e to the power of tan x. So we have that inner function. And if you can identify that inner function, that means you can identify your u. Remember, your u is always the inner function when we talk about it in terms of a composite function. It won't always be that easy to identify it, but if you can identify it, it's a great way to start your question. So because we want to replace x with u, we also want to replace the dx. And we do that by differentiating our u. Now, our differentiation rules are on page 25, and tan x might be one that you may not have seen or seen a lot of, and it goes to sec squared x. Now, you'll notice that we actually have a sec squared x here. So when we bring the dx over, we get sec squared x dx. So I can actually replace this whole thing with our du. And I can replace this part with our u, which makes this so much simpler. So when we can use U-substitution or integration by substitution, it is so straightforward to integrate. So this, we have something really, really straightforward. We have e to the power of u du. So that means e to the power of u does not change. So that's just going to be e to the power of u. I don't need a plus c or anything like that because I have a definite integral. Now here's somewhere where it can go wrong, and that is by plugging in too soon. Please don't. You have to remember that the limits of integration that were given were for x and not u. So what we need to do is plug back in our u, which is tan x, and now we're going to evaluate between pi over 4 and 0. If you're wondering like, well, where does this x squared go? Think of this, because it is the opposite to the chain rule. Like if we had started with this to begin with, we would have differentiated it, which would have just stayed e tan to the power of tan x, multiplied by the derivative of tan x, which is x squared. So that x squared was brought into this when it was differentiated. So when we work backwards, when we integrate, that's where we got rid of it. So this is going to be e tan pi over 4 minus e tan 0. If you've skipped any of the video, I did go through why we have to use radians in our integration and in calculus in general. So it's really important that we remember that they are in radians. I prefer, if possible, to use page 13. So the tan of pi over 4 is going to be 1. The tan of 0 is going to be 0. So we end up with e to the power of 1 minus e to the power of 0, which is e minus 1. And that is our answer. So integration by substitution is actually a little bit easier than integration by parts. However, you don't have a formula. It is something you need to remember yourself. And what I would say is when we're working through questions, it's one we look for before we look for integration by parts. So before I finish off our last few examples, I just want to kind of touch on something that will be more important when you get to differential equations. But it is important, I suppose, to start thinking about it now, because integration, generally students find it absolutely fine when we're told we are now on a section and you are doing integration by parts and you know it's integration by parts and you can apply it. Or then I say, here we're in a section with integration by substitution, you know that's what we're doing and you can apply it. But when I give you an integration question and I don't tell you which technique to use, that's where students tend to fall down. It's like, how do I identify which technique to use? So we've now met a number of different ways to integrate, and hopefully you are or will become good at doing each type. But in a question, the method for what method for integration should you use? And this is where identification is key. So we really only have 3 ways. You have your basic rules, which is basically look at page 26. You have your integration by parts and you have U-Substitution. So what I suggest you do is use this checklist. And the checklist is in a very specific order. So the first thing I would do in a question is check, is there a formula on page 26? And if there is a formula, use it. Okay? We have very clearly talked about which kind of versions of these formulas you might be able to work with. So like a version of 1 over x that may be backwards chain rule, cos x tan x. Okay, they're the one, cos x sin x. They're the ones you might be able to kind of apply a little bit more to it. But generally we're talking just basic formulas on page 26. The next thing to check is it a composite function? So actually, I would check for composite function next. And if yes, use integration by U-Substitution. So that's integration by substitution. So that's the second thing I would check for. And then the last thing, and it is the last thing, is try integration by parts. So this is the messiest. And there are cases, and we'll see them in a second, where integration by parts will work. And you know, you are going to not just be asked to do these, but do these under time pressure. So I've often looked at questions with students and worked them through, but a question that could be half a page with U-Substitution could be 4 or 5 pages with integration by parts. So it's not that it's not possible to use integration by parts, it's just time consuming. And if we can use U-Substitution, we try to use that instead. Now, integration by parts, remember, it is about multiplication. So it is about 2 bits multiplied together. So, you know, sometimes we can't get away from it and we just have to use it. But getting to grips with this little checklist and looking at each question and thinking, would I identify that if I were given this in exam? It's so good, so helpful. It will stand to you. Especially keep this checklist beside you as you move into differential equations. So here's example 11. So here's one that I think can be a little bit tricky, and I've put in kind of 2 tricky ones on purpose for the integration by substitution. And I say tricky, I mean tricky to identify that they're U-Substitution. So from an identification point of view, that can you see this as a composite function? And like majority of students might be like, Not really. Maybe. So the fact that it's a square root, so the square root is x to a power. So that's like a bracket to a power, but in it is an x squared plus 1. That's why it's a composite function. But it is harder to see. Now here's an example where I've been asked in the past, can you change that to x squared plus 1 to the power minus a half and use integration by parts? Absolutely. Do you want to? No. Okay, integration by parts will work in theory, but you do not want to approach it. It is not the most efficient way to work. You will not have the time to do that in an exam. You need to be able to identify this as integration by substitution. So is there a substitution that you could use? And the answer is yes. We have the square root of x squared plus 1, so we can identify, maybe after a little bit of practice, that this is my inner function. A really kind of nice way to identify the fact that this is integration by substitution and not integration by parts is something I mentioned when we did integration by parts. And that's this in LATE, so in latte, whatever way you want to say it. If I were to say to you, here is integration by parts, we end up with two algebraic pieces, okay? So both the top and the bottom line are algebraic. So remember I said at the end of this slide earlier on, if both parts are the same, so both algebra, for example, then we have a more suitable type of integration to use, and that is integration by substitution. So bear that in mind. I just want to draw your attention to it because it is the kind of thing that actually maybe in an exam you might go, oh my God, I never thought about that deeply enough. So let's go back and actually start working with that. So our inner function here is what's under the line and under the square root. So our u is going to be x squared plus 1. Then we're going to differentiate that. So we get du dx, and that gives us 2x. So we're going to have du equals 2x dx. Now, all I have to kind of take out with my dx is an x. Okay, so I don't want that 2 there. So I'm going to bring my 2 back over the line and have a half du equals x dx. And now I can replace. So I'm going to integrate between root 3 and 0. So we have our definite integral. I'm going to put a half du up here, and that's the square root of u on the bottom. So we manipulate the du dx line, so these lines here, until it's something that we want. So I only want the x dx together. So I'm just going to tidy this up a little bit so it's a little bit kind of easier for us to manage. So that is 1 over 2 is on the bottom and the root u is on the bottom, and then we have du. So in terms of what that is, it's a half. Bring the root u over, that's u to the power of minus a half du. When we integrate that, we add 1 to our power and divide by our power. So the half sits there, it's a coefficient. We add 1 to our power, so that's power of a half. Then we divide by a half. Be careful, sorry, this should be gone. Be careful when you're dividing by a half. Dividing by a half is the same as multiplying by 2. So here we have a half on the top and a half on the bottom effectively. So u to the power of a half, we want to make sure before we do any substitution, remember our u we put in, those limits are for x. So we're going to do back substitution, which means we're going to plug back in. So that is the square root of x squared plus 1. And we're going to evaluate that between root 3 and 0. So that is the square root of root 3 squared plus 1. And then we're going to take away the square root of 0 squared plus 1. That is 3 plus 1, which is 4. So we get 2 minus 1. And our final answer is 1. So here's our last example of the video. We're looking again at integration by substitution. This is probably even tougher to see as a composite function. And the reason it is a composite function is we're actually looking in our log tables. Look at your page 26. And the function we're focusing on is 1 over x. And the version we have here is actually 1 over x plus 2. So this is, we kind of looked at a few of these earlier on. If you just had 1 over, how you're using your log. This one has an x in the top as well. So that's why we're going to use the U-Substitution, because it'll be a little bit trickier. But effectively, that bottom line, that is our u. Okay, again, a hint why you definitely wouldn't use integration by parts. It's both algebra, so it's really about focusing on what would be sensible as my inner function. So you want to take something quite complicated to simplify the integral. So by taking u, then du dx is just 1. So du equals dx. Now, this then doesn't give us something particularly nice, because we end up with x over u du. But we still have an x, which we don't want. So we have to be a little bit clever with that. And we're going to go back to this line here, because I can write my x in terms of a u. If I rearrange this line, it becomes u minus 2, meaning this is what my integral becomes. Now, looking at that, you might go, how is that any simpler than what we started with? And the answer is because we only have one thing on the bottom. So we have a u, one term, rather than x plus 2 that's in the original. This is much simpler because we can integrate, and this is something you should be familiar with in maths because we don't have any fancy integration techniques. You would have hopefully learned how to break out your polynomials like this. So rather than writing these as one single fraction, we're going to write them as 2 different fractions. You can only do that where there's a single term on the bottom. We couldn't do that like here. That is not the same as x over x plus x over 2. That's not how that works at all. Okay, so think about if you were adding these fractions, how common denominator, and then you just bring the top lines together. So we just need to be a little bit clever. Don't automatically assume it's not substitution just because you're struggling to get rid of one of your terms. Really think about, how could I be clever here? Where could I write x in terms of my u? So I now have something much simpler. It is 1 minus 2 over u du. And actually, I'm going to rewrite, instead of 2 over u, let's write that as 2 u to the power, actually no, sorry, we'll leave it as 2 over u because that's as it's in the log tables. So then integrate 1, that goes to u, minus 2 over u, that is like 2 times 1 over u, which is going to be 2 ln u. You can put in those absolute values, that's absolutely perfect, and that's between 6 and 0. Remember, we are not plugging in for u, you're plugging in for x. So let's replace our u with our x, and that's ln. Because of our values, I'm just going to write that as x plus 2 without the absolute value signs, because I know we're plugging in a 6 and a 0, which is fine. And then we're going to evaluate that for 6. So 6 plus 2 minus 2 ln 8 minus 0 plus 2 minus 2 ln minus 2 ln 2. And this answer, we want to write it in the form p plus or minus ln q. That plus or minus means it's one or the other. So tidying that up, we get 8 minus 2 ln 8 minus 2 plus 2 ln 2. I'll just write that out again so we can see it really clearly. So that is 8 minus 2 ln 8 minus 2 plus 2 ln 2. Now, I have a p, so 6. That part's fine. I have a constant on its own, but then it should be plus or minus a log, which I don't have at the moment. So first thing I need to do is think about my rules of logs and how I can maybe clean these up. So the first issue is the coefficients. So I'm going to get rid of those and write them as powers. So that's going to be ln 8 to the power of 2, which is 64, plus ln 2 to the power of 2, which is 4. I'm going to use my rules of logs. Subtraction means division. So that's going to be plus ln 4 divided by 64. And that's going to give me 6 plus ln 1 over 16. Now, slight issue here in the sense they told me P and Q both had to be natural numbers. So what I'm going to do with my natural log here is I'm going to flip it, and that's going to make it a minus. So I get 6 minus ln 16. So what I could have done here is I could have put the 64 over the 4 and made it negative. I'm just going to bring this part over here and explain it a little bit more for anyone who is not so comfortable with the logs. So all I've done here is I've said, well, that is the same as ln 16 to the power of minus 1. And then I put the minus 1 in front, which is simply minus ln 16. It's a nice little trick to know and to have.